4.6, we were looking at variation of parameters. And what variation of parameters takes into consideration is that sometimes we have functions on the right side of our differential equation that don't work very well with undetermined coefficients. In the method of undetermined coefficients, we dealt with functions on the right side that were polynomials, exponentials, sine or cosine. But if we got outside of that scope, then we ran into problems. And we said that undetermined coefficients did not work very well for those particular problems. So if we review those methods, we found out that our particular solution was related to the function that we have on the right. But we also found out that sometimes our homogeneous solution was related to the function on the right as well. So when we were getting our particular solution, we needed to know our homogeneous solution first. And if the function on the right did not look anything like the homogeneous solution, then we just wrote our particular solution generically based on what f was. But sometimes, if the function on the right was related to the homogeneous solution, then our particular solution, of course, we would have some arbitrary constants out front, but we would have to pick up some power of t times the function on the right, or times our homogeneous solution, because they were related to each other. So depending on how many times what our roots were to the homogeneous part of this differential equation, that determined how many t's we needed to pick up out front. And that worked really well when we had functions on the right side that were polynomials, exponentials, sines, or cosines. But if we don't have those particular functions, just multiplying by a t may not get us where we need to go. So what we can do is we can suppose that we're always going to have some relationship between the function on the right and our homogeneous solution. So our homogeneous solution is going to always be in the form c1 y1 plus c2 y2. And of course, y1 and y2 depend on what the roots of our auxiliary equation are. If the function on the right is polynomial, exponential, sine, or cosine, and our function on the right mirrors the solutions to our homogeneous, then we had to pick up t squared, something like that. But if we have other functions on the right side, if we're going to maintain this relationship between that function being related to the homogeneous, then there may be some function that we can multiply our solutions by that will produce solutions to our particular solution. So if we're saying that y1 is the solution to the homogeneous, there may be some function, let's just call that v1, that we can multiply out front by that will give us a solution to the particular. So instead of multiplying by t or t squared to get a related function, we might have some other function that we multiply by. And the same thing for y2. Y2 is a solution to the homogeneous. If it's related to the particular solution, then instead of multiplying by t squared, something like that, there might be a different function that we have to multiply it by to relate it to our function on the right. If the function on the right is not a polynomial, not exponential, or sines or cosines. So we're going to try to take this and we're going to try to derive some way to find out what V1 and V2 need to be so that this generates a solution to our differential equation. So if this is going to be a solution to our differential equation, then when we take the first derivative and second derivative and plug this and those derivatives in, then we have to come up with a true statement. So let's take our derivatives. So our first derivative, we have a product here. Y1 is a function. V1 could be some function instead of just a constant. So we'd have to do the product rule. So that would be the derivative of the first times the second plus the first times the derivative of the second, and the same thing for the second term. The derivative of the first times the second plus the first times the derivative of the second. So to keep our second derivative from having a second derivative of V1 and V2, which would make things pretty messy, let's try to avoid having a second derivative of V1 and V2. So in order to do that, let's rearrange this. Let's put V1, Y1, V1 prime Y1, V2 prime Y2, V1, Y1 prime, V2, Y2 prime. And notice if we were to take a second derivative, then for this particular part, if we take the derivative of this, we would have products here. And when we take the derivative of this first piece, the derivative of this first derivative would give us a second derivative of V1. Likewise, we would have a second derivative of V2 over here. So to avoid that, we can force that part to equal 0. We can make it a requirement that V1 prime Y1 plus V2 prime Y2 is 0. So if that's the case, then Y prime is just V1 Y1 prime plus V2 Y2 prime. So now when we get our second derivative, it's the derivative of the first term, so V1 prime Y1 prime, V1 Y1 double prime, V2 prime Y2 prime, V2 Y2 double prime. So using the product rule on the first part, we got these two terms. The product rule in the second part, we got those two terms. So now we have our second derivative, and we have our first derivative. So we can substitute these two along with our arbitrary function here into our differential equation. So let's take these and substitute into our differential equation. So we have A times this one. Let's see if we can copy this. Oops. So this is our second derivative. So we have A times all of this. Then we have B times our first derivative. So our first derivative is here. So copy this. We don't need this stuff out front. That's just letting us know that this is the first derivative. So B times that. And then C times our function, which was V1 Y1 plus V2 Y2. And that equaled F. F is what is our function on the right side. So let's group some things together. Let's group the V1 terms together, the terms that are the V1, not V1 prime, but just regular V1. So this is a V1, this is a V1, and this is a V1. So V1 when we distribute the A, we would have A times that. So if we take the V1 out, then we would have A Y double prime. We have B times that. So if we take the V1 out, we would have B Y prime. And then here, C times Y1. So then let's look at the V2 terms. So we have a V2 term here, here, and here. So if we group the V2 terms together, we would have A times this one. So the V2 is out front. A Y2 double prime. B times this one. The V2 is out front. So B Y2 prime. And then here, C Y2. And then that leaves us with this term and that term. So A times V1 prime Y1 prime plus V2 prime Y2 prime equals 0. So let's remember real quickly that Y1 is a solution to the homogeneous equation. So if we plug Y1 in, if we plug Y1 along with its derivatives into this, if Y1 is a solution to the homogeneous, that means when we add all that together, we get 0. So this, when we add that together, that makes 0. Same thing with Y2. If Y2 is a solution to the homogeneous, that means when we substitute Y2 and its derivatives into the left side, that should equal 0. Because remember, the homogeneous differential equation has a 0 on the right side, but the same coefficients on the left. So that leaves us with A times V1 prime, and this is not 0 over here. For our differential equation, we have an F on the right side. So we have A V1 prime Y1 prime plus V2 prime Y2 prime equals F. And then we have another equation that I'm going to put above this one. Remember, we required something to equal 0 earlier. We required this to equal 0. We required V1 prime Y1 plus V2 prime Y2 to equal 0. Notice both of these equations have V1 prime in them. Both of them have V2 prime. Those are unknown values. Those are things that we are looking for, but we don't know. Y1 and Y2, those are solutions to the homogeneous equation. So for a particular differential equation, we would be finding Y1 and Y2. And hence, we would also be able to find Y1 prime and Y2 prime. So our unknowns in this set of equations are V1 prime and V2 prime. Of course, if we could find V1 prime, we could find V by integrating. Same thing with V2. So let's simplify this a little bit by dividing the left side by A on, and hence we'd have to do the right side by A. So that's going to give us, let's copy the top equation down, V1 prime Y1 plus V2 prime Y2 equals 0. If we divide the left side by A, that leaves us V1 prime Y1 prime plus V2 prime Y2 prime. So let's highlight, and for the, let's see, for the bottom one, I keep on writing 0. That's not 0. That's F over A. So let me make sure I wrote it correctly. So this one here, the bottom one, if we divide both sides by A, we have this part. So V1 prime, Y1 prime, V2 prime, Y2 prime. So if we highlight our unknowns, these are our unknowns. These are what we're looking for. So this is just a system of equations. Our coefficients are, this is something we know, this is something we know, this is something we know, this is something we know. So in terms of a system of equations like that we normally do, 3x plus 5y equals 11, x minus y equals 1. 3 and 5, those are the things we know, like we know y1 and y2. X and y, those are the things we don't know. So that's like our v1 prime and our v2 prime. So when we solve this system of equations, we're looking for x and y. When we solve this system of equations, we're going to be looking for v1 prime and v2 prime. So the easiest way to do that is to use Cramer's rule. I illustrated in a video that you should watch before you watch this one, is how we solve a system of equations that might not be quite so conventional. So if you haven't watched the Cramer's rule video, pause this, go watch that Cramer's rule video, and then come back. So we need to write 3 determinants. We need to write one determinant that lists the coefficients on the left side. So the coefficients on the left side, if our variables, if the things we're looking for are the v1 primes and the v2 primes, then our coefficients are y1, y1 prime, y2, and y2 primes. Even though those are letters right now, those are going to be things that we have access to for a specific problem. When we take this determinant, we multiply diagonally, so y1 times y2 prime, and we subtract this diagonal product, so y1 prime times y2. So that's D. We need a determinant for v1 prime. So that determinant comes from replacing the coefficients in the v1 prime column with the right side. So the right side is 0 and f over a. So we replace the first column with that, and we keep the other column. The coefficients in the second column, y2 and y2 prime. So that determinant, if we multiply this diagonal is 0 minus this diagonal, we could call that f over a times y2. And then we need a v2 prime determinant. So just like we did the v1 prime determinant, we're going to take our v2 prime column, which is the second column, and we're going to replace that with the right side. And we're going to leave the first column alone. So the coefficients on the first column are y1 and y1 prime. So when we calculate that determinant, we multiply diagonally this way. So that gives us f over a times y1 minus that product, 0. So we get this. So to get v1 prime is the determinant of v1 prime over d. So that's minus f over a y2 over y1 times y2 prime minus y1 prime y2. And to get v2 prime, that's the determinant of v2 prime over d. So that's going to be f over a times y1 over y1 y2 prime minus y1 prime y2. So all of these are going to be things that we will know for our specific differential equation. A is the coefficient of the y double prime term. F is the function on the right. Y1, Y2, those are the two solutions to the homogeneous differential equation. And of course, if we know y1 and y2, we can get y1 and y2 prime. So then to get v1, we simply integrate this. So A is going to be a constant. That's going to be a number. So we can pull the negative and the A on bottom out front. So we're going to have the function times y2 over y1 times y2 prime minus y1 prime times y2. We're going to integrate that with respect to whatever our independent variable is. And then v2, we're going to integrate v2 prime to get v2. So this is v2 prime. We're going to pull the a out front. So we're going to have 1 over a out front. And when we integrate, we have f times y1 on top, y1, y2 prime minus y1 prime, y2 on bottom. And we're going to integrate that with respect to our independent variable. Could be t, could be x, could be whatever. So this will give us v1 and v2, which are going to be functions that we multiply our homogeneous solution by to get our particular. So v1 times y1 and v2 times y2, that'll give us our particular solution. Remember, our homogeneous is c1y1 and c2y2. So let's work through an example. Let's suppose we have the differential equation y double prime plus 25y equals 3 secant 5t. So 3 times secant 5t. So this is our f of t. So let's find our homogeneous solution to begin with. So y double prime plus 25y equals 0. So our auxiliary equation is r squared plus no r's plus 25 equals 0. Subtract 25 from both sides, and we get r squared is negative 25 square root. So r is plus or minus 5i. So what does that mean for our auxiliary or our homogeneous equation? That means our homogeneous equation doesn't have an e because a is 0. So it's c1 e to the 0t, so no e's, cosine 5t, plus c2 no e's, sine 5t. So that's our homogeneous. So then that means that our particular solution, we need a v1 and v2 such that v1 cosine 5t plus v2 sine 5t will be our particular solution. So in other words, our y1 is cosine 5t and our y2 is sine 5t. So we're going to use the formulas that we came up with here to try to get v1 and v2. So we have y1, we have y2. Those came from our homogeneous solutions. So we need to get y1 prime and y2 prime. So y1 prime, the derivative of cosine is negative sine. So negative sine of 5t times the derivative of the inside. y2 prime, the derivative of sine is cosine times the derivative of the inside. So we're going to take those pieces and remember that f for us is 3 secant 5t. We also need a. A is the coefficient of y double prime. So in this case, that's 1. So with those pieces and these formulas, we should be able to find v1 and v2. So let's see if we can copy these formulas over. So here is the formula for V1, and it didn't copy the integration symbol. So V1 is minus 1 over A is 1, times the integral of F. What was F? F is 3 secant of 5t. All of that over Y1 times Y2 prime minus Y1 prime. Y1 prime is minus 5 sine 5t times Y2. And then integrate that with respect to t. So out front, negative 1 over 1, that's negative 1. On bottom, let's notice that we have a 5 here, and negative times negative, that's going to make a positive, a 5 there. So we have a 5 that's a factor that we can pull out. Now, we can't pull a 5 or a t or a 5t out from the inside because these are inside the function, but this is a coefficient, that's a coefficient, so we can take a 5 out front. We could take it out front on bottom, on the inside, or we could take it out front on bottom on the outside. So that's just the coefficient. Let's take it out front on the outside. So what's that going to leave us with? On top, let's take that 3 on top out front. So if that 3 is gone, that leaves us secant 5t on top. On bottom, that leaves us cosine times cosine, so cosine squared. That double negative changed to a positive. We're left with sine times sine, so sine squared. So negative 3/5 out front. Recall that sine squared plus cosine squared, as long as the angles match, sine squared plus cosine squared is 1. So that denominator reduces to 1. So we're just integrating secant 5t dt. So we have the integral of secant u du. We just need to make our u and du match. So if u is 5t, then du would be 5 dt. So we need to pick up a 5 here, and we need to pick up another 5 on bottom out front. So that'll just give us negative 3 over 25, and this will be the integral of secant u du. Well, that's not an integral that most of us carry around off the top of our head, so we can go to our integration table and find out, well, what is the integral of secant u? So the integral of secant u is natural log absolute value of secant u plus tangent u. And then, of course, normally we have a plus c there. So this gives us V1. V1 is this. We still need to get V2. So V2, let's copy the formula for V2. So to get V2, this is the formula. Back over, oops. Where I slid, I don't need to slid. So paste. Oh, hit the right button, wages. We're going to integrate that. So we have 1 over A. A is 1. Our function out front, remember that was 3 secant 5t. So that's F. And then Y1, oh, this is, we made a mistake in the last one. We're going to have to go back and fix. In the last one, we did not multiply times Y2 on top, did we? We took care of everything else, but we did not multiply by Y2 on top. So unfortunately, this is not quite correct here. So what do we need to pick up? So y2 is sine of 5t. So f, this is f, y2 is sine of 5t, and we got this other. So what we saw happen is still going to happen. The 5 is still going to come out on bottom. The 3 is still going to come out on top. We have a negative. We still have cosine squared plus sine squared, which is still going to be 1 on bottom. But instead of just secant 5t, we have secant 5t times sine 5t dt. So let's move this stuff. Remember that secant is 1 over cosine. So instead of writing this as secant, we could call this 1 over cosine. So that's going to give us cosine 5t on bottom. Sine over cosine is tangent. So instead of integrating secant like we did, we actually need to integrate tangent. So tangent, let's see. If this is u, we need a 5 here to go with our du, and we need to pick up a 5 on bottom there. So we have a negative 3 over 25, and then we need to integrate tangent u du. Of course, that may not be a formula that you carry around off the top of your head, but remember that the integral of tangent is negative natural log absolute value of cosine u, where u in this case is 5t. So that means V1 is negative times negative, that makes a positive 3 over 25 natural log cosine of 5t. So that's V1. Now let's get V2. So we've replaced A, we've replaced F, Y1. This is a mistake we made on the other one. We didn't put a Y2 in. Y1 is cosine of 5t. So in place of Y1, we're going to put cosine of 5t. Remember when we made this substitution, we ended up with a 5 that could come out front. And then we had a cosine squared plus sine squared, so all of that was over 1 dt. This denominator is the same denominator that we had when we were looking for V1. That's the same denominator. And that denominator, when we simplified all of it, we had cosine squared plus sine squared. That made 1, and we pulled a 5 out front. All right, so see where that's going to lead us. Oops, that's the wrong. Where'd it go? That's the wrong button. So V2 is 1/5. Pull the 3 out, so actually 3/5. The integral, we don't have a fraction anymore because that's 1 is gone. Secant 5t, we could call that 1 over cosine 5t. If we multiply this times that, notice this cosine 5t is on top, that cosine 5t is on bottom. So those cancel. The 3 is gone, so everything is gone except 1 dt on the inside. So when we integrate that, when we integrate 1, we pick up a variable. So V2 is just 3/5 t. So what are we looking for? We're looking for our particular solution. So our particular solution, remember, is V1 Y1 plus V2 Y2. So V1 is 3 over 25 natural log absolute value cosine phi t times what was y1. Y1 was cosine phi t. V2, so 3/5 t, times y2, which was sine phi t. So that's our particular solution. We already found the homogeneous solution earlier, which was what? C1 cosine phi t plus C2 sine phi t. So if we need our general solution, it's just the sum of those. That's a homogeneous solution plus the particular solution.